Hi, hello everyone. So again, this is the video dealing with section 3.4, exponential and logarithmic equations. And this is the second part of the section video dealing with solving logarithmic equations. So different from the exponential equations, the log equations are very easy to solve. The technique is always the same for every type of question, which is we're going to uh, isolate the log expression, and then we'll proceed. Now, but before we do so, right, again, this is a review from Math 119, and let's just remind you what a log equation is. So a log equation is any equation with an unknown variable inside the log, okay? So for example, this would be a linear equation. If I put now the variable inside of the log, this becomes a log equation. Okay, so these are the equations that we have to deal with. And the technique to solving them, it's always the same. Okay, your textbook gives you, you know, a procedure to do so, but I'm gonna show you a shortcut based on the log properties, which is better for us. So the first step would be to isolate the log expression in one side. Now, when I mean log expression, I mean the log expression where the variable is located. So that has to be isolated I'm going to do it on the left side. So you're going to isolate the log expression. And then two, we're going to exponentiate both sides of the equation. Okay. And then we're going to solve the remaining equation. Solve the remaining equation. Now, log equations are similar to the rationals, similar to the absolute value equations, where we have to check the solution that we got to see if it works with our answer. It may not work, so we have to check always. Now, sometimes you're going to see a situation where, and this is on step one, that we have more than one log expression in one side of the equation. If that's the case, these log expressions must be condensed into one before we can proceed. So that's what we mean isolate. Not only that we move all the expressions to one side of the equation, but they have to be condensed into one. Okay, you see an example, and then we will exponentiate both sides and solve the equation, and then we're going to check. So here are the four steps. Isolate the log expression, exponentiate both sides, you see how, solve the remaining equation, and then check the answer. These are the four steps. Okay, so let's take a look at the examples I have for us. Okay, so these are all of the possible types that you can see. So the first A and B are the easier ones. And then we have a situation where we have to condense the log one way, and then last example, condense the log another way. All right, so let's begin with type A, the first one, right? So I have log base 4, x plus 3 equals 2. So we take a look at the log equation. It's an equation because the variable is inside the log argument. And I have to solve this. So this is the technique that we employ. The technique is we'll look at the base and we'll exponentiate both sides of the equation using this base. So this is going to be, don't write this. This is, I'm going to show you a shortcut in a minute. Using this base, will exponentiate both sides. So 4 becomes the base. And by the properties of logs, this 4 will cancel with this 4 right here, and I'm going to be left with x plus 3. Okay? So this is the shortcut. Instead of doing this every single time, this is what you will do on an exam. Right? So here's the base 4. This 4 becomes the base of the other side. These two will cancel. On the left side, I am left with x plus 3 and then 4 squared. Okay? This base goes to the other side and becomes the base of this number, which now becomes the exponent. Okay, this is all review from Math 119. I evaluate 4 squared, obviously. And now I have a simple linear equation. This is my answer. Okay? In this particular case, I don't need to check, but I will check. All we are interested in is to check if log expression is valid. Now, what does that mean? It means that the answer I obtain, I have to go back here and determine if once I replace x with this value, the value inside of the argument is positive. It has to be positive, otherwise it's not valid. So in this case, 13 plus 3, it's 16. That is perfectly okay, but if you wanted to fully evaluate, you could, right? So log base 4 of 16 is 2. Obviously, 2 is equal to 2. Okay, but I don't need to go through all of those steps. All I need to do is, here's the original log equation. All I need to do is this, grab the answer, replace x with it, and check if the argument is greater than 0. If it is, you are fine, and your answer is valid. The reason for this is the domain of logs are positive numbers. I cannot have inside of the argument 0 or any negative number. Okay, so the first case, very, very simple. All of the other cases are done exactly the same way. Let's see the second case. Here's another log expression, equation, because the variable is inside of the argument. So the very first thing I need to do, the log seems to be isolated on the left side, so this is a good starting point. But I cannot have this number 3 here, so I have to first divide both sides by 3. Okay, so now they cancel. Now also understand the following thing. Let me just write it over here and then I'll just delete it. So here's natural log 2x divided by 2. Okay. This 2x is inside of the log. It will not cancel with the 2 right here. So don't do this. Okay, this is very incorrect. This number 2 would only cancel if there was a 2 as the coefficient. All right. In addition, okay, natural log over 2 is not the same as natural log 2x over 2. This I can obviously simplify here, okay? This one I cannot. All right, so make sure you understand from your previous course the difference between the two. Okay, so I've simplified. I divided both sides by 3. I have this now. Now, natural log, you remember, it's log base e. So if you want, you can write this as log base e so you can see exactly what's happening. So it's the same technique that we used to solve this. What did we do? We exponentiate both sides using this base. We're going to do the exact same thing here. Instead of 4, I have a base e that goes on the other side. Now these two will cancel. I have 2x equals e to the fourth, right? This will become the new exponent. And then I divide both sides by 2. Okay, you don't need to evaluate e to the 4. This is perfectly fine as my final answer. And now I have to check, right? But I don't need to check the exact numerical answer. It's a soft check where I grab this value, go into the original equation, I replace x with it, and all I need to make sure is if the argument is greater than 0. Well, so it's 2 times e to the 4 over 2. So it's e to the 4. This is definitely a positive value, so this is good, which means that this is good. So this is my solution, e to the 4 over 2. Okay, soft check. All right, let's do the next one. Same techniques, but now notice that, for example, 7, I have 2 expressions dealing with logs. So that could be a problem because I cannot begin the procedure this way, right? Yes, it's true that the log expressions are isolated on the left side, but they have to be condensed. In other words, I have to have only one log expression in here. So what do? So we apply the property of logs that the sum of two logs is their product. So these two, log base 2 of x and log base 2 of x minus 7, becomes log base 2x times x minus 7. So this is absolutely necessary. You cannot begin otherwise. Now I have a single log expression on the left, and I'm ready to begin. Just as before, it's the same technique that we use here and here. We're going to exponentiate both sides of the equation using this base. So this number goes right here. The 2 becomes the base, and 3 becomes the exponent. So, and then this will cancel with that. I will end up with x minus 7. Notice that after the exponentiation, the log expression disappears. And I have 2 to the third power on the other side. Now this becomes a simple quadratic equation. All right. X squared minus 7x equals 8, minus 8 on both sides. And now you can solve it whichever way you want to solve it. Let's see if we can factor this, right? So this is a quadratic equation. We can solve by completing the square. Probably completing the square will be a little harder because the middle term is an odd number. Quadratic formula, or we can see if we can factor. So let's see if we can factor. If it's possible, great. If not, we use the quadratic form. So the product has to be 1 times C, right? Product 1 times C, or minus 8. And the sum has to be B, which is minus 7. So the only ways that I can get an 8 is with an 1 and an 8, or 2 and a 4. And then you adjust the sign. Now, You looking at these two pairs, only at these two pairs. Professor, how about 4 and 3? Yeah, 4 and 3 can give you a 7 if both are negative, but when I multiply them, I don't get 8. So this is out. It has to be only among the pairs you got for the product. So it's something to do with a 1 and an 8, right? The 2 and the 4, the gap is too close. So the only way I can get a -7 by adding 1 and 8 is if I do what? +1 -8, right? And when I multiply them, I get back the -8. So perfect. So I'm going to rewrite the middle term using these two numbers, +1x -8x -8 equals to 0. Okay. So I factor by grouping now. X plus 1 minus factor 8, x plus 1 equals 0. Notice that x plus 1 is a common factor, so I'm going to pull it out. And I'm going to end up with x minus 8 here equals 0. Now, by the zero product rule, I set this factor to 0, solve for x, set this factor to 0, solve for x. Obviously, very simple at this point, -1 on both sides. +8 to both sides. I got two answers. They both have to be checked in the original. So I go back to the original and check. But notice that this is a soft check. I don't need to check if both sides are equal to each other. All I need to check is domain greater than 0 inside the log here, right? This has to be greater than 0. This has to be greater than 0. So notice that for the -1, once I replace x with -1, this already fails. So this answer is already out. It doesn't even matter if it works on the other side. Doesn't matter. So the -1 is out. I'm going to check the 8. So replace x with 8. Yeah, that's positive, so that's good. Replace x with 8. 8 minus 7, 1. Yeah, that's positive, that's good. So the only answer I have is x equals 8. So if this is a question on the exam, we would want to see all of this work that you see here. And then we want to see that you eliminated x minus 1. And the only answer is +8. Okay. Also, don't think that always the answer is the positive one because it's not always the case. So you have to check them both. All right. So this is the case where we had to condense the log using the product property. Let's take a look at the last question, which is similar to this one, but a different, we use a different log property. So last case. Again, I have two we have two logs on the left side and I have a log on the right side. So I have to, on this side here, I have to condense the logs. Okay. But now I have a minus. So we group him or we condense him in the quotient. using the quotient property. And now it looks pretty good because now look what happens. I have a natural log on the left and natural log on the right. And if you wanted to, you could, just for you to see that this, even though it looked complicated from the beginning, right? It could write log base E, log base E. So now can you see that you have the same base on both sides? So when we exponentiate, all of this disappears. So I am left with a linear equation so far, maybe a quadratic. I end up with this, right? And this is because I had also log here, here, and here. So now what can you do? You can cross multiply if you want, right? So cross multiply upward, right? So the x is going to multiply the x plus 2, and the 4x plus 3 is going to multiply the 1, which is just 4x plus 3. Now, obviously, distribute the x. And I know that this looks like a quadratic, so I'm going to move everything to the left. So minus 4x and minus 3 on both sides. I got 0 here. I got x squared minus 2x minus 3 equals 0. All right. We just make it a little bit smaller and move it to the side. So this is what I have to solve now. So the original log became a quadratic equation. So we'll solve the quadratic equation, try to do it the same way. You can do it by completing the square quadratic formula or by factoring. I think this is factorable. So A times C, right? 1 times negative 3. So remember, this is A, this is B, and this is C. This is like a review from Math 119. And the sum has to be B, which is negative 2. So I need two numbers whose product is negative 3. Oh, the only one that involve integers is 1 and 3. And for me to get a sum of negative 2, I have to have positive 1, negative 3. So I found the pair. I'm going to rewrite the middle term using these two numbers I have. So plus x minus 3x minus 3 equals 0. And then I factor by grouping. Okay, so x plus 1 minus 3, x plus 1. X plus 1 is a common factor. I factor it out. And in the second parentheses, I will get x minus 3. So again, I'm left with two terms to apply the zero product rule. So set this to 0, solve for x, set this to 0, solve for x. So obviously, x plus 1 equals 0, x minus 3 equals 0, minus 1 on both sides, plus 3 to both sides. So again, I got two answers. I have to go back into the original, and I have to replace both x's inside their values, inside their variables. And if I have to have a value greater than 0 inside the log. So let's begin with the negative 1. So when I replace negative 1 here, negative 1 plus 2 is positive. It's okay. When I replace it here, the 4x plus 3, I get negative 4 plus 3, which is negative. So this is already out. I don't even have to bother with the second one. Now let's do the 3. So I go back into the first expression. 3 plus 2, 5, okay. I go into the second, 4 times 3, 12 plus 3, okay, that's okay. And 1 over 3 positive, that's okay. All right, so 3 is the answer. Now you may think, well, it's always going to be the positive. No, it is possible that none of these may work. Possible. So if that's the case, you would write no solution on a problem, right? But in this case, again, the positive answer was my answer. And then you would just say x equals 3, making sure it's visible that you remove the one that failed. Okay. So we don't need to see the check, but we need to see that you were able to cancel one of the choices and clearly indicate that the solution is, in this particular case, x equals 3. So this is how you solve these log equations. You're just going to isolate the log expression and exponentiate both sides of the equation with the given base. So in the first case was base 4, and then base e, and then in this case base 2, and then in this case base e, but because I had a log on the other side, both bases cancel. Okay, so I review from Math 119 for this topic 3.4, solving exponential and log equations.